Okay, hello everyone. I welcomes to all in our lecture series on superconductivity. In this lecture series, we are going to discuss these topics. These topics are very much essential for B.sc, B.Tech, M.sc, M.Tech and various entrance examinations. In our last two classes, we have been discussed already with a detailed note introduction part of this superconductivity, Meissner's effect and mathematical explanation of Meissner's effect or the so-called validation of negative magnetic susceptibility. In this class, we are going to discuss London's equation and London penetration depth. Okay, so let us start. In our previous classes, we discussed these things. This is the introduction part of the superconductivity. Last class, we discussed Meissner's effect. Meissner's effect told that if a superconductor in superconducting state, then it will expel the magnetic flux, which is called as the Meissner's effect or the so-called diamagnetic nature. But by considering the zero resistivity theory, we found magnetic flux is constant. So Meissner's effect or the so-called diamagnetism, perfect diamagnetism and zero resistivity are contradicted with each other. That we discussed in our last class. Finally, we concluded what? We concluded that superconductivity is not only a diamagnetism but a new type of diamagnetism. And this new type of diamagnetism will is going to be explained by London's equation. Later, this superconductivity is explained by BCS theory that we are going to discuss in our forthcoming lectures. But in this class, we are going to discuss London's equation. Let us start. In 1934, London brothers F. London and H. London proposed a theory to explain the Meissner's effect and zero resistivity, both Meissner effect and zero resistivity of a superconductor which is in superconducting state. They derived two equations, two famous equations to explain Meissner's effect and zero resistivity, which are known as London equations. According to this theory, superconductor is composed with normal and superconducting electrons. What is that? Here, this is the detailed proposed or imagination by uh, or assumption by London brothers. Here, above critical temperature, superconductor is composed with only normal electrons. Considering this situation, this is a superconductor, okay, which is in normal state. That means above transition temperature. So all the electrons are called normal electrons. This is the assumption by London brothers, right? This is the assumption, okay. These are the assumptions. Below critical temperature, superconductor is composed with both normal and superconducting electrons. So this is the situation that is represents superconductor is in the superconducting state. That means below transition temperature. So in this state, the superconductor composed with normal electron and this star symbol represents the superconducting electron. But with decrease of temperature below Tc, the concentration of superconducting electrons, that is your Ns represented by N subscript S, increases. At 0K, all normal electrons transformed to superconducting electrons. So below Tc up to 0K, this is the things already we have been discussed, that with decreasing temperature at a particular temperature, the resistance of the superconductor will be 0. So below Tc towards 0K, the normal electron starts to transform to superconducting electron, and at 0K, all the normal electron transformed to superconducting electron. That means a superconductor which is at 0K, that means it is composed with only and only superconducting electrons. So these are the assumptions by London brothers. With these assumptions, they given two equations which will explain both Meissner effect and zero resistivity. Okay, so here they considered m is the mass of the electron and super electron also, minus E is the charge of electron, normal and superconducting electron, Ns is the concentration of superconducting electron, that means superconducting electron per unit volume. Concentration of normal electron, Nn, that means normal electron per unit volume, right? Vs is the drift velocity of superconducting electron, is the applied electric field. Suppose consider this state. If I am going to apply a electric field, this is the positive and this is the negative terminal, then electrons will be dragged towards this side with a velocity that is called the Vs, drift velocity of superconducting electron. Obviously the electric field will be along this direction, right? Now we are going to consider Newton's second law. Newton's second law tells that motion of charged particle in a conductor is written in this format: m into dv by dt, or m into a acceleration equal to qe minus resistive force. This is the normal conductor. Okay, consider this is the charged particle. So electric field applied along this direction. Electric force will be applied along this direction, that is your EE, and it will be dragged along this direction. Electron will be dragged along this direction, right, with a velocity v. When it will dragged along this direction, the resistivity or the resistive force will be along this direction. This is the resistive force direction. So what will be the equation? The equation will be acceleration, m into acceleration, that is m into rate of change of the velocity, will be equal to QE along this direction. Resistive force, E is the along this direction, QE is along this direction, resistive force is along this direction. So it will be QE minus resistive force. Okay, but if we are going to consider superconductor in superconducting state, then superconducting electron could not feel or perceive any type of resistive force. So resistive force for this case will be 0. That means this part will be 0. Then this equation will be how much? M into dVs. Vs stands for drift velocity of superconducting electrons. Vs. M, rate of change of superconducting velocity, drift velocity, equal to this force. Q is the charge. So for the electron, it will be minus E into E vector. The current density in general, we know this one. In case of superconducting electron, the concentration will be written as Ns. E the charge, V is the drift velocity of superconducting electron. This is your equation number 1. Now consider the derivative of equation number 1 with respect to t, both the side. Then what we can get? D by dt of Js equal to minus Ns E dVs by dt, right? Here dVs by dt, how much we found? Here dVs by dt we found minus EE by m. That I am going to substitute over here, minus EE by m. That implies rate of change of current density or current density due to superconducting electron will be equal to Ns E square by m into E. This is your equation number 2, which represents London's first equation. Now we are going to go for London's second equation. For that we are going to take the curl of this equation number 2. So left hand side will be d by dt of del cross Js, right hand side will be del cross E. Del cross E is nothing but minus d by del B by del T. That is the third Maxwell equation, electromagnetic equation, Maxwell. So instead of del cross B, we can substitute minus del B by del T here. So this right hand side will be minus Ns E square del B by del T by m, right? So finally we found del cross J here. Del cross J will be equal to, see, Ns E square m all are constant. So here d by dt, change of rate of change of time. This side of rate of change of time. If we are going to integrate with time, then we can found this one. Del cross J will be equal to minus Ns E square by m B. This is your equation number 3, right? Then B, we know that B equal to del cross A, where A is your magnetic vector potential, magnetic vector potential, that we know, right? Hence equation number 3 can be written as del cross J will be equal to minus ns E square by m. Instead of B, what we have to write? Del cross A, right? So cancelling the curl both the side, we found Js current density due to superconducting electron in superconducting state of a superconductor. This one will be equal to minus ns E square A by m. Let this is your equation number 4, and this equation number 4 is called as London's second equation. Okay, now we are going to go for explanation of Meissner's effect and flux penetration considering London's equations. For that, we considered Ampere's orbital law. Actually, we know the Ampere's orbital law is this one: B dot dl equal to mu 0 I. By using Stokes' law, this can be written as del cross B uh, surface integration equal to mu 0 I. So del cross B equal to, this is the integration surface, that means area. So it will be mu 0 I by A or mu 0 J. This one I written directly. This is also nothing but your fourth Maxwell equation itself. Fourth Maxwell equation, right? So considering Ampere's circuital law, we can write this much. Just take curl both the side. Curl both the side of this equation. Del cross B equal to mu 0 del cross J. This is the representation of vector triple product, right? Vector triple product means, suppose considering A cross B cross C is nothing but what? Is nothing but B into A dot C minus C into A dot B, right? You just compare this with this one. Here A is the del, B is the del, C is the so-called B. So here B means del, I written over del. A means also del. C means B vector, del dot B. Similarly, this will be A dot B means del square, del dot A, del dot A, del dot del. Del dot del is nothing but del square, and C vector is nothing but so-called B, so del square B. Just using the vector triple product, we can write this one mu 0 del cross J. This del dot B represents the Maxwell's second law. Maxwell's second law. That means divergence of magnetic field, which is always 0, because due to absence of magnetic monopole, that we know well. So this value will be 0. So what we have write? Minus del square B. If this value will be 0, then it will be minus del square B equal to this much. Same thing it has been written. Also I written the cause due to del dot B equal to 0. That implies minus del square B equal to mu naught del cross J. Already we found value here. Del cross J, this value, by considering equation number 3, right? Here I have to write by considering equation number 3. From equation number 3, here from equation number 3, we just substituted minus, here minus n square E by mb minus, yes, minus e square m by into b. From equation number 3 we just substituted over here. That implies here minus minus got cancelled. We found del square B equal to this much. Del square B equal to this value is written as 1 by lambda square into B. Let this is your equation number 5. And here lambda is equal to less than. This lambda is the function of temperature itself. And here this lambda represents below transition temperature. Any temperature below transition temperature, this value is how much? Here you can see lambda square is nothing but this much, right? Okay, sorry 1 by lambda square is this much, so obviously lambda will be just reverse m by mu not ns e square root over. Okay, you just remember this expression is most important expression. Upon this expression, you can face a numerical in your exam. Just remember, most important expression, right? This lambda is called as your London penetration depth. London penetration depth. In general, from experimental studies, various experimental studies, it has been found that lambda is a material property, and its range varies from 300 angstrom to 5000 angstrom. It is also one of the most important information that you should always remember. Lambda value varies from 300 angstrom to 5000 angstrom. Okay. Okay, now we are going to consider the 1D, one dimensional expression of equation number 5. This is the 3-dimensional expression. We know that del square is your del square by del x square plus del square by del y square, the Laplacian operator. But consider only one dimensional equation of equation number 5. Okay, or one dimensional format of equation number 5 will be written as, along x-axis if we are going to consider, then this del square b is written as del square b by del x square, along x-axis only, 1 by lambda square into b. Here it is written in the form of magnitude. This is in the it is both magnitude and direction. Here it is written only in the form of magnitude only. D square b by dx square equal to 1 by lambda square into b. Let this is your equation number 6. Okay, so then general solution of this equation number 6 will be what? A1 e to the minus x by lambda plus a2 e to the x by lambda. How? We know del square y by del x square minus m square y equal to 0. Suppose we have a differential equation like this, then let this is a square. Okay, a square. Then its auxiliary equation is nothing but m square minus a square equal to 0, m equal to plus or minus a, and the general solution is your a to the minus ax plus b into e to the plus ax. Okay, so if I'm going to compare this equation with this one, instead of a we can write 1 by lambda. So here if I'm going to put instead of a 1 by lambda, then it will be written as e to the minus x by lambda, and instead of a here we have been written a1, instead of b I have been written a2. Let this is your equation number 7, which represents, this equation number 7 represents the general solution of equation number 6. Okay, here a1 and a2 are the constant, can be found by applying boundary conditions. Here you can see the term a2 into e to the power x by lambda in the equation number 7 represents the increase of magnetic field strength from the edge to inside the superconductor, which is in the superconducting state, which is not possible. What is the meaning of that? Here you can see. Here suppose this is the superconductor. Okay, practically just imagine, whenever we are going to apply the magnetic field, due to the Meissner's effect, the magnetic field strength gradually decreases from the edge of the superconductor towards the inside of the superconductor. So consider this one, this axis is your x-axis. So as much as you are going to move from the edge towards inside the superconductor, you can found the strength of the applied magnetic field is going to decrease gradually. Okay, but by considering this equation, this term in equation number 7, which represents increasing the magnetic field strength, which is not acceptable. So this term is not going to consider for the solution of this equation number 6. So the new solution will be by discarding this term. We found b equal to a1 e to the minus x by lambda. Let this is your equation number 8. From this equation, it can be found that when x equal 0, when x equal 0, if I'm going to put x equal 0, x equal 0 means here you are standing over here, okay, just as the at the edge of the superconductor. This is the 0 at x equal 0. Magnetic field strength is maximum. Let b naught. Okay, so if I'm going to put x equal 0 over here, so e to the minus 0 a1 will be equal to b naught. That implies a1 equal to b naught, right? So at considering this boundary condition, that at x equal 0 the maximum value is b naught, then equation number 8 will be further going to be modified, and the new equation will be b equal to b naught e to the minus x by lambda. So this is one boundary condition, this is another boundary condition we have been applied, and we found the final solution of the equation number 6. Let this one is your equation number 9. B equal to b naught e to the minus x by lambda, which is the solution of this final solution of this equation number 6. Okay, okay, okay. Now we are going to define the London penetration depth, that is your lambda, by using equation number 9. How? Here you can see. Consider x equal to lambda. At x equal to lambda, you just consider at x equal to lambda in this equation number 9, what we can find, b equal to b naught by e. So here we from this expression we can define that London penetration depth is defined as the distance from the surface of the superconductor. This is the surface or edge of the superconductor, which is in the superconducting state obviously, at which magnetic field strength decreases to 1 by e of its original value. So at the edge, the value is how much? B naught. After this distance, if we are going to move, then the value will be reduced to B naught by E. So this distance is called as your lambda. So this is the definition. You just remember, or you just try to understand, or you just remember this figure. Automatically with your language you can define this definition, exam. London penetration depth is not constant. It is a material property that we know, and it varies from 300 angstrom to 5000 angstrom, that we know. It is a material property. For one material it will be 300 angstrom, for another material it will be 5000 angstrom. It varies. It is a material property. Now we are going to consider case 1 here. Just try to understand. Case 1, we consider superconductor. Consider a superconductor which is in a superconducting state obviously, having a thickness much less than that of its penetration depth. Suppose the uh, penetration depth of a superconductor, suppose 400 angstrom. 400 angstrom, right? This distance is your 400 angstrom, suppose, and we consider a situation or a material whose thickness is less than, this is the thickness here, this is the diameter or the thickness of this superconductor. Now we are going to consider thickness which is less than that of this penetration depth. That means this thickness. Consider this thickness, right? If I'm going to consider this thickness of the superconductor, or thickness much less than that of its penetration depth. Penetration depth is this much. I consider the thickness this much as less than that of this penetration depth. Then here you can see that in this length the magnetic flux almost seems to be constant, but above that it is decreases. As much as we are going to move inside the superconductor, it is decreases. This is the graph what we explained, the equation number 9 here. This is the graph that at x equal to 0, this is the at x equal to 0, this is maximum b naught. At x equal to lambda, that means this point is x equal to lambda, this value is your b naught by e, and with increase the distance from the edge here, from the edge to inside the superconductor, the magnetic flux gradually decreases, exponential decreases, right? So here in case 1, we found when we are going to consider the thickness of a superconductor which is less than that of the penetration depth, the magnetic field strength inside the superconductor is seems to be constant. Here you can see, here if I am going to consider this superconductor, then it can be perceived that it is decreases gradually. Okay, but if we are going to consider this thickness, in this thickness the magnetic flux seems to be constant. You cannot feel the decrease of magnetic flux in this thickness, right? So mathematically same thing it has been written, when x is less than that of lambda or the so-called penetration depth, then b equal to b naught or approximately constant value. Because here you can see mathematically, suppose we are going to consider mathematically x is very less, x is very less than that of the lambda x. So this e to the power value or x by lambda will be how much? 0. So e to the power 0 will be 1, e to the value will be 1. So if e to the power 0 will be 1, then b equal to b naught. Mathematically also we can write in this way, when less x will be less than that of the lambda. This situation is nothing but your fully penetration situation of the magnetic flux, which contradiction to Meissner's effect. Now consider case 2, in which the thickness of the superconductor is so large as compared with initial thickness. Initial thickness we considered this one. Now in case 2 we consider the thickness is much larger than the initial thickness. In this case 2 you can see that this thickness is much larger than that of lambda or the penetration depth. In this case what is going to happen? From equation number 9 we found b equal to b naught e to the minus x by lambda. So if we are going to consider the situation x is larger than that of the lambda, then this e to the power minus x by lambda will be e to the minus infinity, because x is greater than that of the lambda. So e to the minus infinity means 0. So we can found b equal to 0. So in case 2, when we are going to consider the penetration depth, the thickness of the superconductor, which is in superconducting state obviously much larger than that of its penetration depth, that means x greater than that of lambda, then from equation number 9 we can found b equal to 0. Here you can see, suppose this length, we are going to consider this length. So suppose this is the x, or you consider this length from edge to this length is your x. So at x distance we can found b equal to 0. Here at this much distance, for this case b equal to 0, that means inside the superconductor there is no magnetic lines of force, magnetic flux equal to 0. Only the magnetic flux we can perceive at the edge of this superconductor, this large superconductor. At the edge we can feel up to this much distance. Okay, also from this side also you can consider the same, up to this much distance we can perceive magnetic field, but inside this superconductor the magnetic flux will be 0. So this is the situation of the Meissner's effect. That means this superconductor behaves that it expels the magnetic flux or the so-called perfect diamagnetism. So in case 2 what we consider the thickness is much larger than that of the penetration depth. So hence B equal to 0 due to by considering equation number 9. In this situation, magnetic flux inside the superconductor, which is in the superconducting state, will be 0. That means it obeys the Meissner's effect or expels the magnetic flux or behaves as a dimagnetism. Okay. Case 1 represents the contradiction to magnetic effect or the so-called zero resistivity case, and case 2 represents the Meissner's effect. In this way, London brothers explains the superconductivity, which is a different type of dimagnetism. That is a new type of dimagnetism. Okay, so here I am going to stop this class. In the next class, we are going to discuss variation of London penetration depth with temperature. Thank you so much for watching this video. Thank you.